Hello, everyone, and welcome to today's webinar on 3D vision technologies. My name is Manisha Sherbakova, and I'm a sales engineer here at Teledyne IIS. Today, I will discuss how stereo vision is important to so many robotics applications. I will also touch on what features to look for each application when selecting a good stereo camera. This webinar will be 30 minutes in total, with time for Q&A. Teledyne IIS, or Integrated Imaging Solutions, is under the parent company of Teledyne. Here at Teledyne, we have the slogan of "Everywhere you look," because our portfolio covers a very wide range of products that can be found all around you. Our technology can be found in everyday objects like your cell phone, medical scanners, cameras, all the way up to the International Space Station. Teledyne's wide product portfolio can be split into four main divisions: digital imaging, instrumentation, aerospace, and engineered systems. Our group, Teledyne IIS, falls under the digital imaging division. This group is responsible for products ranging from sensors, cameras, image processors and software, all the way to X-ray and RF systems, LiDAR, GIS, and many other imaging components. Teledyne IIS initially started out as a small team of UBC graduates here in Vancouver who came together to form Point Grey Research back in 1997. Eventually, Point Grey was purchased by FLIR, and FLIR purchased by Teledyne. Our team has a very long history of being leaders in the machine vision space. In 2000, Point Grey came out with the first IEEE stereo vision camera, the DigiClubs. In 2002 and 2006, we released the Bumblebee and the Bumblebee 2, which very quickly became favorites in the stereo vision markets, specifically in academia. Fast forward to 2024, where we have announced our 5 GeV high-precision upgraded Bumblebee X offering. There are several different types of 3D vision technologies available, and which one you go for will depend on your application needs and conditions. They can be broadly grouped into two categories: passive and active stereo. Passive stereo uses two standard area scan cameras placed at a certain distance apart, and the concept of parallax and disparity is used to calculate the depth of the object. Active stereo has several different forms: laser triangulation, time of flight, structured light, and LiDAR. In laser triangulation, a laser is projected onto the surface of the object, and the image of the laser is projected back on the sensor. The displacement in this image gives us an estimate of the depth of the object. Time of flight, as the name suggests, calculates the amount of time it takes for a beam of light to strike the object and travel back to the sensor. Structured light cameras use a pattern projected onto the scene and capture this pattern and estimate the depth using the displacement of the pattern, similar to triangulation. LiDAR systems send out multiple pulses of laser onto the scene and use the concept of time of flight to estimate the depth. So now that we know the different types of 3D vision technologies out there, I want to dive in a bit into why stereo vision specifically is important to certain applications. Passive stereo cameras mimic human vision. Like the human eye, two cameras provide depth perception and spatial awareness, along with contextual information with color and texture. Passive stereo is also capable of high-accuracy depth measurements using precisely calibrated parameters around many points. Unlike certain types of active stereo, passive stereo is robust to lighting variations, texture patterns, noise, and surface reflections. With certain high-performance stereo cameras, you can build a real-time system with hardware-accelerated stereo matching suitable for rapid decision-making and responsive control. The range of distance that a stereo camera can see depends on its baseline, which is the distance between the two cameras. The bigger the distance, the longer the working distance. Using passive stereo, you are able to see over a long range and up to further distances that match human vision. There are numerous applications for stereo vision, ranging a wide variety of disciplines. In today's presentation, I will focus on two main branches of applications: robotic arms and AMRs and AGVs. Robotic arms are used for applications like pick and place, bin picking, palletization and depalletization, among others. Some of the characteristics of these applications are listed here. Usually, the cameras used for 3D vision need to have 0.5 to 5 meters of working distance and be able to work well in both indoor and outdoor lighting. They must be industrial grade and have high accuracy and low latency. If the camera is mounted above the arm, it needs to have a wide baseline. In terms of vehicle applications, we have autonomous mobile robots and automated guided vehicles, which also have similar camera requirements. Because they need to scan a wide area of their surroundings, they usually need a long working distance, up to 20 meters. Some vehicles are outdoor, some indoor, so the camera must be compatible accordingly. Once again, high accuracy and low latency is key for obstacle avoidance. Usually, these vehicles have many other projectors and lighting components on them, so a passive stereo solution is better to avoid interference. As I mentioned on the earlier slide, robotic arms have a few different uses. In bin picking applications, the camera is mounted above and finds the location and position of all the parts in the bin to guide the robotic arm on where to go. In palletization and depalletization, usually the camera is mounted above and finds the position and the size of the pallet payload to be able to instruct the robot on how to pick up and drop off the pallet. In pick and place applications, similarly, the camera is mounted above and finds the position and the size of the object to be able to pick it up from one location and place it at another. In terms of stereo cameras being used on vehicles for navigation, some of the potential applications are autonomous mobile robots, automated guided vehicles, and outdoor robotics. In AMRs, the camera is mounted to the front or the back of an autonomous robot, normally in combination with safety-rated LiDARs. The stereo camera here is used for context and awareness of obstacles. In AGVs, similarly to AMRs, the camera is mounted to either the front or the back of the vehicle, but usually these vehicles follow defined paths and just use the stereo for obstacle avoidance or positioning. In outdoor robotics, the camera is once again mounted either in the front or the back, similar to AMRs and AGVs, and the stereo camera here is used for context and obstacle awareness. The specialty in outdoor robotics is that the surroundings are unknown and more information needs to be mapped. I will discuss this further in detail in the upcoming slides. There are some other applications of stereo cameras that are really interesting and important to acknowledge. In agricultural applications, the camera is mounted behind on either the tilling or the inspection trailer to measure the size or the shape of the crops. In surgical navigation, the camera is typically mounted above the patient and used for positioning information with special markers to ensure accurate positioning. In metrology, the camera is mounted on a robotic arm or fixed above and likely used with a pattern projector for high accuracy measurements. Over the next couple of slides, I wanted to dive deeper into a few of the applications I mentioned earlier, mainly palletization, bin picking, and outdoor robotic guidance. Implementing stereo vision for palletization comes with many challenges, as the field of view has to cover many different angles. Typically, the camera will be mounted on the ceiling with a large baseline so that it can see a large area of the floor. The ceilings in these warehouses tend to be high, so a good wide baseline is crucial. Picking up and placing boxes accurately and gently requires a very high level of accuracy. Time is money in a lot of logistics applications, so low latency in the vision system is crucial so that the robotic arms perform the palletization and depalletization as soon as possible. The next application I wanted to touch on is bin picking. Typically, the camera is mounted above the bin so that it can see the entire bin. The field of view taken into consideration here will depend on the size of the bin you want to image. In this application, high accuracy is crucial as the robot needs to be able to pick up the right object from the right bin with good alignment. To minimize the wait time between pickups, low latency is important. Some bin picking applications, like for package or grocery sorting, might need a color stereo camera, as the color information is used to identify the object to be picked up. The last application I will discuss is outdoor robotic guidance. This application is particularly challenging due to the unknown surroundings and the need to map large areas. In addition, the lighting conditions in the outdoors can change constantly, from cloudy to bright to overcast. This requires a stereo camera with a high dynamic range. The camera must be able to map very long working distances with accuracy, but also detect objects close to the robot for immediate obstacle avoidance. If the camera is not secured inside the robot, it needs to be IP rated and able to withstand harsh outdoor conditions such as heat, dust, moisture, and debris. As the robot may be traveling over uneven terrain, the camera needs to be able to absorb shock and vibration as well. So now that we have discussed various stereo applications and what is important to each of them, I wanted to consolidate all of the factors that one might take into account when choosing a stereo camera. The first one is accuracy. How accurate do you need the measurements taken by the camera to be? The working distance. How far do you want the camera to be able to see? Long life cycle supports. Do you want to be able to design in this camera and use it for up to 10 to 15 years? What about the field of view? How wide do you want the camera to be able to see? In terms of speed and latency, do you want the information to be received in real time? Calibration retention. Would you rather just not worry about recalibrating your camera? Robustness and durability. Would you need your camera to be able to withstand the elements and be IP67 rated? Support and reliability. Would you need to have maybe some technical support along the way while designing in your camera and have a long warranty support in case you need to return or replace some components? I wanted to introduce our new stereo offering, the Bumblebee X, that consolidates all of the factors and the important characteristics that I've outlined in this presentation. The Bumblebee X is an advanced stereo vision solution built on our best-in-class stereo vision portfolio. This new industrial stereo camera comes with the software Spinnaker that offers a comprehensive solution with onboard processing to build successful systems for warehouse automation, robotics guidance, and logistics. Our team's extensive stereo vision expertise and careful attention to customer insights has informed the design of the hardware, software, and processing at the core of the Bumblebee X. With high accuracy across a large range of distances, this solution is perfect for factories and warehouses. The Bumblebee X delivers on the essential need for a comprehensive and real-time stereo vision solution. Customers can test and deploy depth sensing systems that work up to ranges of 20 meters with the wide baseline solution. The low latency makes it ideal for real-time applications such as AMRs, AGVs, pick and place, bin picking, and so on. Some of the key features of the Bumblebee X are noted here. The camera is a factory-calibrated 24-centimeter baseline stereo vision camera with 3 megapixel sensors for high accuracy and low latency applications. The camera is IP67 rated and comes with several ordering options of color and monochrome, different field of views, and 1 GiGi or 5 GiGi PoE. Onboard processing is available on the camera to output a depth map and color data for point cloud conversion and colorization. The camera is also compatible with an external pattern projector and can synchronize multiple systems together for more precise 3D depth information. The camera comes with a software library with articles, example code, and Windows, Linux, and Robotics Operating System or ROS support. The preliminary specs for this product are outlined here. Just for you to note, these specs are still preliminary and can be subject to change. Some of the standout specifications mentioned here are the 3 megapixel resolution, the 24-centimeter baseline, the long range of working distance from half a meter to 20 meters, and the 3 ordering options for the field of view, which are 60, 80, and 105 degrees. This camera comes shock and vibration tested and is perfect for applications where the camera is mounted on a moving component, like an outdoor robot, for example. I wanted to thank everybody for coming to join this webinar with me today, and I hope it was insightful and informational. If you are interested in learning more about the Bumblebee or want to get in contact with our teams, you can give us a call or send me an email. You can also just drop your questions in the chat below or raise your hand, and I would be willing to answer any of the questions you may have. Thank you so much again, and I'm looking forward to seeing you in our upcoming webinars.